Welcome to Real Chemistry with Rothwell. Today, we're going to talk about heating curves and do an example calculation when we try to use one. Looking here, we have a heating curve. Now, this could be the heating curve of any substance, but we'll do water as an example because it's easy to do, and a lot of times students see water used as an example on their homework. What we notice is that there's two distinct sections. There's the growing section where you have this kind of vertical climb, and then you have the flat sections, and they represent two different things. The growing sections actually represent the different phases of matter. So when we look at the growing sections in the case of water, we notice that it starts as a solid, so it's ice, and then it turns into a liquid, and then it becomes a gas. And although it sounds crazy, what's really happening here is that water, initially, if you have ice that's cold enough, you have cold ice, and then you get gradually warmer ice. And I know that sounds bizarre to us, but you realize that if ice is really cold, say something that we can relate to like negative 100 degrees Fahrenheit, well, that's colder than ice that's about to melt at 32 degrees Fahrenheit. And so what we notice is that the ice gets warmer and warmer and warmer until eventually it turns into a liquid. And then we know that liquid water can heat up and it would turn into a vapor, and that vapor could get progressively warmer. Now, the issue then becomes, well, what happens in between? In between, we have, well, the phase changes, and we kind of give them fancy names in chemistry, the phase changes. Rather than calling solid to liquid melting, a lot of times it's called fusion, and we go from liquid to gas. Instead of calling it boiling, we call it vaporization, but generally we want to think of them as the same thing. It's a transition between those states. And so if we look at this flat area right here, we see that we're transitioning between a solid and a liquid. So depending on what direction you're going, if you're absorbing heat, then you are melting. And if you are losing heat, then you are freezing. Now, where this gets complicated and fun is when we want to do calculations with these, because depending on if it's one of the phases or if it's a phase change, we do calculations a little bit differently. For the areas where we have this vertical growth, so the red areas, we can actually use Q equals mc delta T. Where Q equals heat, M is the mass, C is the specific heat, and delta T is the change in temperature. For the areas that have the flat regions, usually the way that we calculate the heat is we say that Q equals N times delta H. Now, this might be a new concept to us, but N is the number of moles, and delta H would be the change in enthalpy. So what we find is that certain phase changes have certain heat required. When we think of enthalpy change, for the sake of simplicity right now, we're going to think of it as how much heat is required, and usually that's measured in kilojoules per mole. So if we get the number of moles of our substance and we multiply it by the kilojoules per mole required for that phase change to occur, then we can calculate the heat for the flat regions. An example problem when we'd have to use this heating curve would be if we wanted to heat 36.0 grams of water, which would technically be ice, from 173 kelvins to 323 kelvins. Now, in order to do this, we would have to change the ice from solid ice to liquid water. So the calculations get a little bit tough. We have to break it into three sections. We have to heat the ice, and then melt the ice, and then heat the water. So for part one, when we go to heat the ice, we have to heat it from 173 kelvins to its melting point, 273 kelvins. So our delta T is 100 kelvins. We would take that and we'd plug it into our Q equals mc delta T, where our mass is 36.0. Our specific heat is the specific heat of ice, which is 2.03, and our delta T would be 100. Now, we need to be mindful of significant figures, and since we start with 36.0 grams of ice, I'm going to do everything to have three significant figures. When we multiply these numbers together, we get 7,308 joules. But if I wanted to round to three significant figures to match the 36.0 significant figures, then I would get 7.30, and I could change it to kilojoules. So I have 7.30 kilojoules. For phase two, we have to melt the ice. This is actually pretty easy. We take 36.0 grams and we convert it to moles. Basically, the way we do that is that we divide it by 18, the molar mass of water. We find that this is 2 moles, and we take the 2 moles and multiply it by the enthalpy of fusion of water, which is about 6.02 kilojoules per mole. So 2 times 6.02 gives us 12.04 kilojoules, and if we were to round to 3 significant figures, that'd be 12.0 kilojoules. Finally, for phase 3, we'd have to heat the liquid water. We have to go from 273 kelvins to 323 kelvins. That's 50 kelvins. Now again, since this is for liquid water, we're going to use Q equals mc delta T. So we'd take our Q, which we're trying to solve for, that's heat, equals mass, 36.0, times C, the specific heat of liquid water, 4.184, times delta T, which is 50 kelvins. Now if we were to put this into our calculator, we would get roughly 7,531 joules, which is 7.53 kilojoules if you round to 3 significant figures. So now I've found the heat required for all 3 sections: heating the ice, melting the ice, and then heating the liquid water. From here, I just add up all those 3 values. We could take 7.30 kilojoules plus 12.0 kilojoules plus 7.53 kilojoules, and we would find that this answer, with correct significant figures, and we need to be careful when we add these numbers, would have 1 decimal place, and my answer would be 26.8 kilojoules. Thank you for listening to Real Chemistry with Rothwell.